Good evening. So welcome to this talk, another day, another billion flows. So my name is Colm. I'm a principal engineer. I work on VPC. I also work on load balancing, and I work on crypto. And what we're going to talk about today is it's all about VPC. We're going to go over how VPC is architected, how it works. And what I'm actually going to do is I'm pretty much going to give the same the same overview of the VPC architecture that I would give to a new hire. Someone just joined the team. Pretty much give this same description of everything, the same level of detail. It's enough to understand how everything's kind of glued together, how packets get from A to B, how all of the seemingly magic stuff that happens in a VPC network actually works under the hood. So hopefully that's going to be really interesting information. Just a bit about myself. So I actually spent the first, so I've been at AWS, this is my 10th year. But before that, I spent the first 8 years of my career as a network engineer. It was my job to configure all sorts of standard networking devices. I spent a lot of time putting labels on cables. That was probably one of my primary network engineer tools. I probably made literally tens of thousands of labels. I'm now very glad that that can just be a description in an API or a CloudFormation template. It doesn't actually have to go physically anywhere. I was in my university's networking society and learned all these things about packets. And so that was the first 8 years of my career. But since joining AWS, I was actually hired to be a software developer. It's really my first software development job. And I write code. That's my main job now. And so now, as a software developer, working on VPC, that's how it's built. It's all built in software. VPC is a software-defined network. It's built on code that handles all the packets, that moves everything around, and so on. We do have a physical network. I'll talk a little bit about that, where it is, which is built by our infrastructure team, and that has traditional switches and routers and all sorts of links inside that. And it's an amazingly impressive system that blows my mind, and the levels of performance that my colleagues in the infrastructure team are able to get out of that network are just staggering, and that's reflected in VPC performance. But we're not going to talk too much about that today. VPC runs on top of that physical network. Okay, so let's just start with what is VPC, right? This is a 400-level talk. We're quite a number of years now into VPC, so people here are probably already familiar, but we'll cover the ground a little. So VPC is essentially a virtual network. So VPC stands for Virtual Private Cloud. And it means customers can essentially draw a virtual box and say, well, that's my network. They get to assign the network range for that. They get to pick it, right? So you can have 192.168 or 10/ or whatever you feel like, whatever makes sense for you. And then inside that virtual network, we can launch things that can talk to each other, right? So we can launch instances. Regular EC2 instances that you can log into, use, run web servers, all of those kind of things. Run containers. You can launch RDS databases or your own databases. And these days, all sorts of other cloud resources, right? And those can all be launched directly into the VPC, into subnets and so on. They're under your control, all via APIs. Those resources get IP addresses that make sense in the context of that network. So if your VPC is using 192.168, then the IP addresses for these things inside your VPC all start with 192.168, and it all kind of makes logical sense. Very much emulates a traditional data center network, whether it was just a physical network or something built with VLANs and so on. You can connect this network to other networks, right? So we have our Direct Connect product, where you can now interconnect the VPC to, say, an on-premises data center, so you've got machines there. That's why it's so important that you can pick the IP range for your VPC, because once you start interconnecting all these networks, all of the IP ranges have to be deconflicted, right? So in our VPC, we're using 192.168, which means elsewhere we have to be using something else. And we can connect, we also have a VPN product, so you can connect this to, say, your office and be able to access VPC resources over private IP addresses from your desk at work, which is pretty important. I recently realized just how important that is. I had an opportunity to sit down with a customer and watch how they did their software development, and it really struck me that native connectivity helped them out a lot, because they were running unit tests and connecting to resources that were all hosted in the cloud, and the fact that they could just do that on their desktop really sped things up for them. It was really, really important. It's not just about like everything on the business side being able to talk to each other. It's also really critical for developers. Because you can connect all these networks, right? We also have support for routing tables. So this virtual network, this VPC, you can create routes inside it, or routes, as some people say. I always say routes, and I say Route 53 for what it's worth. And if anybody ever disagrees with you, you can always ask them how the song Route 66 goes. It's clearly root. That just solves the argument right there. And well, you can set routes inside the VPC so that you can say this prefix goes here, this prefix goes there. I need this network to go to this direct connect link that actually goes to my on-premises data center or whatever, and this network goes over VPN out over here through a VGW, which is a virtual gateway. And we've got internet gateways if you need to get to the internet, and NAT gateways, and all sorts of other things that I'll talk about later. Okay, so this is all fairly familiar, probably. This is kind of standard networking in the context of a VPC. As of this year, you can also do something else with all this, which is instead of just using IPv4, you can use IPv6. We have support for that now. It's routing a different different version of the IP protocol, but as far as everything else is concerned, it's the same. And because this is a software-defined network, right? Everything I've talked about, unlike having to physically plug cables in anywhere or get on the ground and label things, it's all under programmatic control via APIs, right? So I can create these route entries, I can launch instances, I can assign IPs, and so on, all programmatically, right? Just call APIs to do it. I can template those things. I can put them in CloudFormation templates or use other templating tools to build automation. I've seen teams that can instantiate entire VPCs with hundreds of resources in them, and then tear it all down and do it again if they need to, which is pretty amazing. Because all of that's going through APIs, it also means we get change history and audit capabilities. We plug into the things like AWS config and so on, so you can and CloudTrail, and you can see when your network is being changed. There's lots of strong controls there. There's layers of authentication built in because it's all web services APIs. As a network, right? Just as a virtual network, we build in some things beyond just traditional like IP layer, routability, and so on. We have built-in support for DHCP, right? So we actually assign IP addresses to instances and so on using DHCP. And there's some programmatic control for that. You can control a few things about how the DHCP is vended. We have a built-in DNS service. Every instance or container can use our DNS resolver fleet to resolve things. And that includes support for private DNS. So if you can create a private domain in Route 53, and you can say, this resolves in VPC A, also VPC B, VPC C, and so on, and only resolves there. So you can do things like split views if you need certain domains to resolve to private IPs. You can do that. It's all built in, including support for health checks and failover and everything else that comes with Route 53. That's pretty cool. Actually, one thing I should mention, which didn't quite make it into the talk, because it literally launched just a few hours ago, but today we announced support for inter-region peering, which I know people have been keen to get for a while. So you can now peer VPCs in multiple regions. I'll explain in a bit more about peering. But But one of the cool things is actually Route 53 private DNS works across regions. So you can actually use a private DNS view with Route 53, tag that zone with a VPC A in region A, VPC B in region B, and it works. It just works. You can have these private lookups that span regions. And now those regions can talk to each other using inter-region peering. It's pretty cool. So the network also comes with a built-in firewall, right? So we've got support for network ACLs and security groups, which are just two control mechanisms that let you allow or prohibit traffic on a source destination basis. Security groups is it's also an abstraction that lets you manage collections of instances and so on. Say they're all in the security group, and this security group should be able to talk to that one and so on. I mean, you could build your own firewall, right? You could run something like IP tables or do that on your own instances. But the beauty of having this on the network, right, is that it gives you that additional layer of protection. If the box were ever, if the software in the box were ever compromised or something like that, there's nothing the attacker can control that would influence the firewall, which is pretty important for a security control. So that's built in. You can use it. And then we also support jumbo frames, which just means we can support large packets larger than 1,500 bytes. So a lot of networks, they support up to about 9,000 byte MTUs. That's like a really common number, just based on what was common in some network vendors' chips, about 10 or 15 years ago. We actually vend a 9,001 byte MTU, just because we believe in giving that little bit extra. Just wanted to give it away. So that's why you get 9,001. Every VPC is free. We don't charge for them. So we see a lot of customers who really just have one or two VPCs. They maybe have this is my production VPC, this is my pre-production VPC, or this is something I'm testing out, or this is a different team or whatnot. But we're starting to see more and more customers who actually have quite large numbers of VPCs, who really do a lot of segmentation, who say, this application should get this virtual network, this one should be over here, and they kind of treat VPCs like these little isolated playpens where they know things can't just reach across easily, and so they get a level of isolation, which is pretty cool. And so that's about having many VPCs at once in parallel. We also see customers now who use VPC as part of immutable infrastructure patterns, who, like I said earlier, create a VPC, get it in the state they want, but then tear it down because they move on to the next iteration of their software deployment or whatever, and they want to do the whole thing at the level of the whole network because they find that works, which blows my mind. It's a pretty amazing architecture to see built. Especially common with container architectures, right? It's kind of amazing. Okay, so that's my high-level spiel on what VPC can do, how it all works, at an IP routing level, what's going on, what the features are. So how does it all work, right? What's going on to actually make this function, right? So let's start by giving away a little secret about how EC2 works, which is that your virtualized instances that you can run and use and log into and so on, well, they actually run on physical hardware somewhere, right? There is a real box in a data center somewhere that virtual machine is running on. Okay, big reveal. And those those physical hosts host one or more customer instances on them. And in that physical host, right down there, kind of at the layer where the hypervisor sits, or even below it in hardware, is a virtual router, right? In every EC2 physical host that's there. On our latest platforms, the things we've been launching for the last several years, like Peter DeSantis talked about on Tuesday, that uses our Nitro platform and other hardware platforms that have been developed here. So that's basically like a hardware embedded router that's in those physical hosts. And then on older platforms, things that were launched years ago, it's kind of an emulated software router that's running down there with the hypervisor. It's kind of an abstracted virtualized service. And that router is doing all of the magic of making VPC work, right? So we provide these virtual, isolated networks. Customer A can be using 192.168/16, and customer B can be using .168/16. They can both be using it, both are overlapping. It all just works, right? So clearly we're not just taking those packets and putting them on the wire, right? We got to disambiguate them in some way. There's a lot of networking technologies for that, right? VLANs, VRFs, you could use MPLS. There's a lot of ways you can build virtual networks. We looked at all of them when we were building VPC. None of them scale to our needs. All of them are, they can get dangerous at scale, and we were designing for millions of VPCs, very, very, very high numbers. So we do our own proprietary encapsulation to disambiguate everything, right? So if you were to look at a packet on the wire, you will see ordinary IP on the physical network at the outermost layer. And those packets are flowing between those physical hosts using that amazing physical network that my colleagues in the infrastructure team have built. And that's just relatively mundane networking. It's just IP A to IP B, and traffic finds its destinations in the usual ways. There's not too much magic going on. It's an intentionally simplified network. We focus a lot on performance and resilience and creating a lot of magic in our platforms for that at that level. But we don't do too much like network trickery. There's no routing tricks or anything like that going on. And then just above that layer, we have the VPC encapsulation protocol, where we stamp our own data on the packet so that we can disambiguate things. There's information in there like which VPC this traffic is for, which ENI, so that's an elastic network interface. That's kind of the physical interface equivalent that we attach to instances and so on. That's in there, and there's enough information though so that when a packet goes from one physical host to another, the physical host that receives it, knows what ENI on what instance that traffic is for. It can read the data that's in the encapsulation and it can send it where it needs to go. And then on top of that, it's just your normal IP packet, right? Like what your instance sent, right? And that's if you're familiar with looking at TCP dump or digging into IP headers and all that stuff, that just looks normal. Okay, so this is for traffic between like two instances, right? So the two instances are on two physical hosts. This is how they communicate. But we can send traffic elsewhere, right? We can send traffic off network, right? We can send traffic to the internet. We can send traffic to Direct Connect. We can send traffic to VPN and so on. And so how does that work? Well, we have these things called Blackfoot edge devices. So Blackfoot's a platform we built quite a while ago, which essentially translates from the inside VPC network, with this encapsulation, to the outside, normal IP networking, right? So it too has, an embedded router essentially, although really you could kind of think of the whole thing as a really big router, and can encapsulate and de-encapsulate this traffic, unwrap it, can also do some other tricks, and it can send the traffic to and from a bunch of destinations. Blackfoot's this really cool system. We actually named the building I work in after it. So I work in the Blackfoot building in Seattle. That's AWS HQ, basically. By the way, that's a great sign of success, right, for your team. Like, it's a lot of pride. Wow, they named a building after my service. That's really cool. But all of the team members kind of regret that a little, because every time there's an email that mentions Blackfoot, you don't know if they're talking about the building or if they're talking about your service, and your filters stop working, and it gets a little confusing. But it's still awesome that that they named a building after it. That's kind of a cool thing. So Blackfoot takes this encapsulated traffic, right, and says, okay, well, this needed to go to the internet. So it gets to a Blackfoot device. The Blackfoot device will strip the VPC encapsulation. We'll translate the IP addresses, right? So when we go from inside VPC to outside VPC, we got to start using like a public IP address when we're talking to the internet. So Blackfoot will actually do NAT. It'll NAT your internal VPC IP to the external public IP address. That's simple, stateless, one-to-one IP NAT that's going on. Although it's still very, very difficult to do at the kind of scale Blackfoot operates. And then similarly, with Direct Connect, what's happening is Blackfoot de-encapsulates that traffic, passes it on to another network that actually implements Direct Connect, that starts doing things with VLANs, because VLANs are just part of how Direct Connect works. If you have a Direct Connect link, so that's a physical link to one of our Direct Connect centers, you can actually connect to more than just one VPC. And the way that works is it's presented as a VLAN. And so there's some translation in this part of the network where we take the VPC that we got from the encapsulation layer into a traditional VLAN on a traditional physical port and so on. With VPN, it goes to a specialized service that does everything VPN needs, like IKE and IPsec and so on, and applies all that. It's also how S3 and DynamoDB endpoints work. So if you use S3 or DynamoDB endpoints, that's a technology that essentially lets you connect S3 or DynamoDB directly to your VPC without your traffic needing to traverse the internet or a backbone. That is also using the magic of Blackfoot to apply that translation and connect everything together, right? It's pretty cool. So as I mentioned, the outermost IP destination just identifies the target host or where it needs to go. We mark all the packets, but how do we know these, right? How do I know which physical host to send a packet to, right? And that's where this thing called the mapping service comes in, right? And so a mapping service is a distributed service that is in charge of mapping, this ENI in this VPC, corresponds at the moment to this physical host, right? And this instance on that physical host, right? It's basically a gigantic table that has all that information in it, right? And it also manages routes. So if you've got, if you've got a routing lookup, it's not just a host that you're getting to. It's saying, oh, this traffic should get to the internet or whatever. The mapping service will say, well, this IP prefix needs to go to Blackfoot for internet gateway or whatever, right? That's what's going on. And so the embedded routers down here are talking to the mapping service and figuring out, okay, well, for this virtual destination, here's the real physical destination, right? And it's not really like any traditional network lookup protocol that you may have seen before. It's not like ARP, say, right? It's much more nuanced, and it's been refined over the years, and there's a lot of cool stuff going in there to make sure that lookups are really, really fast, right? So it wouldn't work. It wouldn't get the kinds of performance we need for an instance to say, okay, I need to reach this IP, and then the embedded router to go, well, I don't know where that IP is. I'm going to ask the mapping service, and then the mapping service tells it, and then we can send the packet. That would just take too long. We have a really fast network. Things aren't that far apart. You can now get latencies between instances that are measured in tens of microseconds if you're using enhanced networking in ENA and so on. And we can do that to our mapping service and so on. We can get fast lookup times, but it's just not scalable. We would be absolutely hammering the mapping service if that's how it worked, right? If we're that naive. So mappings they're both pushed out and preloaded, and there's caching patterns, and there's all sorts of things in there to make sure that the mappings themselves are highly optimized and that lookups happen very quickly, so that we can go from an instance needing to send a packet to being able to look up that mapping directly in memory, encapsulate the traffic in the way we need, send it on to its destination extremely, extremely quickly. It's a key to how it works. It's so like I said, mappings are cached where they're used, which means we have to proactively invalidate them and so on when they change. And that's what's going on, right? That's the mapping service. That's how that part works. Okay, we're going at lightning speed here, but I know we're keeping up. So far we've essentially covered how packets get from A to B, right? How a lot of the VPC technology works. And in previous versions of this talk, this is kind of where we stopped, right? This is kind of, okay, that's how VPC works. That's what's going on. But the title of this talk is there's another billion flows, right? So what about flows? And why are we talking about flows? So if you look closely at what the VPC network is capable of, there's a lot that's going on that actually relates to flows, not just packets, right? So some examples, right? So when you use security groups, those are actually firewall rules that include stateful connection tracking, right? And we have flow logs as a feature where we give per ENI aggregated, data that you can see your traffic going around, but you can see that it's aware of flows, right, to an extent. We launched Network Load Balancer 2 months ago. That's a new load balancer offering that's kind of embedded and meshed into the VPC architecture. And the reason you can tell that it's embedded and in the VPC network itself is because it, unlike previous iterations of our load balancing products, it can load balance traffic to your backends and targets transparently, right? So you can create an NLB and you can put targets behind it, instances, containers, or IP addresses. And let's say it's an internet-facing NLB, a public NLB. It gets traffic from out there on the internet. Your instances and containers actually see the remote, IP address of the actual client, like the browser, whatever it was out there on the internet. It just comes in, right? There's like something in the way doing the load balancing, clearly, because we pick different targets each time, but yet the flow is preserved. All of the details of the flow are preserved. It's not acting as a proxy, right? Which is how most traditional load balancers work, including most appliances, right? Most load balancers, terminate a TCP connection, decide where it should go, create another TCP connection that comes from the load balancer, right? And if you want to see what the original source was, you have to use like an X-forwarded for header or a proxy protocol header or whatever, or a SIP header that some appliances have, right? But that's not what's going on. This is actually in the network, right? So there's clearly some flow awareness. And NAT gateway, right? So we have this native gateway type in VPC that can do many-to-one NAT, which has to be stateful, right? Mapping hundreds, thousands of instances to one IP address just requires state and requires flow tracking. So clearly there's some flow tracking going on in the VPC network, right? And it turns out that's really important for how VPC works these days, right? So this flow tracking, a lot of it's actually happening on that embedded router that's on the physical host that I talked about, right? And so this is a 400 level talk, so I hope we're okay with the next slide. We're actually going to look at what flow tracking actually involves a little. So just as a quick refresher, right? A flow, so we consider a flow to be a 5-tuple, right? It's the combination of a protocol, like TCP, UDP, ICMP, a source IP, a destination IP, a source port, and a destination port, right? That's a flow. So when I connect to www.amazon.com, my browser picks a unique source port. No other source port that source port is not being used, and certainly not being used to talk to www.amazon.com at the moment. So it gives that to my browser, and then my browser starts essentially creating all these packets which match a 5-tuple like this, and that's how my traffic gets to www.amazon.com. That's how www.amazon.com can send packets back to me and have it go to that tab in my browser and so on. That's how everything's disambiguated, right? That's what a connection is. That's what a flow is. And so with TCP, right, there's this really, with both TCP and UDP, there's this really important property that like the 5-tuple has to be completely unique, right? Like we would start mixing packets between senders and receivers and so on if it weren't completely unique. So if you have, say, the same instance, right, like the source IP in this case, 192.0.2.1, trying to connect to the same destination IP on the same port, so port 443 here, that's the HTTPS port. They have to be disambiguated in some way, right? So they have to use unique source ports. So if they're coming from the same instance, the instance will handle that. The Linux networking stack will say, OK, this connection gets port A, this connection gets port B. And there's some other stuff going on too, right? So, standard TCP handshake, client sends a SYN, server SYN-ACK, then we get an ACK going the other direction, and now we can talk. There's some other numbers floating around that are important. The first in starts off with a sequence number, right? That's random, that the server will know then that its replies are correct and everything's nothing's being manipulated in the middle. And there's an ACK number too. So when those ACK packets come back, they have an ACK number that was invented by the other side. And when you're doing flow tracking, right, all of these things matter. So what you want to do is you want to make sure, okay, well, the security group rule said this traffic's allowed, this connection's allowed. So when we see the first packet, it matches that rule, and it's allowed in, right? Now we could just say, well, when we see the second packet, all right, well, if it matches the security group rules, it's allowed in. But we don't do that, right? We do something a little better, which we say, well, when that second packet comes in, its sequence number should make sense. Its ACK number should make sense, like relative to the previous one, right? It should be within the TCP window, all that kind of stuff. And that's to prevent, certain kinds of attacks where people will just spoof traffic and try to, have it come in and pretend to be in the middle of a TCP connection and so on. You can't spoof traffic on the VPC network. There's lots of anti-spoofing measures, including all that encapsulation I told you about. But internet traffic out there on the Wild West internet may be getting spoofed. So it's important that happen, right? So that's the kind of state tracking that's happening down there. For UDP, we don't have sequence and ACK numbers to track, but we do have these things called datagram IDs. So UDP packets can be fragmented, right? So if a UDP packet is too big to fit inside that MTU, it'll actually be split across multiple fragments, and those fragments have to be reassembled. And to do that, they've got IDs, and those have to be relative, and they have to make sense. And all that has to be tracked, and we have to be able to reassemble everything and make sure that arbitrary fragments that have nothing to do with anything don't just make it to an instance, right? That's part of what's going on. And for ICMP, we also have a really complicated case. So ICMP is the Internet Control Messaging Protocol. You probably most know it for ping. You ping something, you send an ICMP echo, you get an echo reply. But it's also used for signaling errors related to connections. Things like path MTU discovery, like a packet gets too far in the network and says, oh, I don't fit anymore. An ICMP response will be sent saying, no, it didn't fit. You need to change the size. The way that works is that, well, you get back this ICMP error message that actually includes a snapshot of the headers, at least, of the packet that triggered the error, right? And so for ICMP, you actually have to do something really deep. You have to go look all the way down there and see, well, does the ICMP error reference a packet that makes sense, right? That is something that I previously allowed or sent and should come in, right? And so that's what's involved in stateful connection tracking. That's what's happening, down there under the hood, right? And so far, like that we're doing that, kind of makes sense of, okay, well, now kind of makes sense how security groups work, right? We're just doing all that contracting. It makes sense how we can kind of aggregate flows at the ENI level. We have this embedded router that can at least say, well, all these packets are related, and so in this time interval, we only really need to send you one line of information about that, not, a million lines. But how do the others work, right? How does network load balancer and NAT gateway work? So one observation is that if you look at these two things, right? If you look at NAT gateway and NLB, they're super similar, right? They're really about letting many instances share an IP address, right? So NAT gateway is about saying, I've got all these instances, they want to get to the internet, but they want to hide behind one IP. Or maybe I've only got one public IP, right? Super common. That's what NAT gateway is. NLB is the same, just in the other direction, right? I've got all these instances, I want to hide behind one IP address, but in this time I'm accepting connections. Getting connections in from the internet, say, and deciding where to put them. So they're really the same problem, right? And so to solve this, to build all this, we built a system called Hyperplane, which Peter introduced and talked about on, or last night, on Tuesday night. And just introduced a bit about it. I'm going to cover it just in a little bit more depth. And so Hyperplane, right? It's there on the VPC network, along with EC2 physical hosts and Blackfoot and so on. Actually, Hyperplane nodes are regular, like completely normal EC2 instances. So the team that runs Hyperplane, they just launch instances, and they have a special privileged API that can make them Hyperplane nodes. But as far as they're concerned, they can launch, they can scale, they can do everything an EC2 instance can do, and they use the EC2 network in the same way everything does. And even though these are handling huge volumes of traffic, we actually get amazing performance out of them. So these are doing, accepting traffic. They are, we'll talk a bit in a minute about what they're doing with that traffic, but they're essentially doing state tracking and routing the packets and so on. But because the underlying EC2 network now, because that physical network has these, tens of microsecond scale latencies, it's no trouble at all. It can actually do quite amazing amounts of throughput and responsivity and not add much latency by doing this architecture. It's pretty amazing. So if you provision a Hyperplane resource, so that's NLB, NAT Gateway, Private Link, which launched for customers and partners yesterday, and EFS, the Elastic File System, also uses Hyperplane under the hood. The mapping service essentially says, OK, this ENI, it's really a Hyperplane thing. Send it to Hyperplane, right? Hyperplane's going to handle that. And then when the traffic comes to Hyperplane, so I said it's a distributed system, right? There's some magic going on. Those Hyperplane nodes are actually making transactional decisions about how to handle your packets. So when that first packet for a flow comes in, before there's any state setup, Hyperplane has to decide what should happen to it, right? So for example, in the case of NAT, Hyperplane has to guarantee that outbound connection will have a unique source port. At least if you've got two connections, both going to www.amazon.com on port 443, Hyperplane has to guarantee in a transactional way, like really robustly, that those connections have two different source ports. That's really important. And that's basically a database problem. Like trying to guarantee transactional uniqueness is a distributed consensus problem, right? And we do it all in memory. That makes it a little bit faster. At least we don't have to commit things to disk. But it's still a distributed consensus problem. And that's what Hyperplane's doing, like in real time. So when that packet comes in, all the nodes collectively are figuring out it gets this source port, and only it gets that source port. And then they robustly commit that state. So when the next packet comes in, we know what source port it should have, and the traffic can all flow without interruption. It's pretty amazing. Now, it might seem like that's not that common. Like, how many times are you going to get more than one or two boxes hitting the same IP address port at the same time? Well, software updates are a pretty common case, right? So like 1 in the morning, all these Ubuntu boxes wake up and say, we're all going to hit the same Ubuntu app repository at the same time. It's like the worst case you can imagine, like literally hundreds, thousands of instances all deciding, we want to get to this one IP address on the same port at the same time, right? And Hyperplane has to work like to make sure that those port allocations are unique and do it in a very small window of time, right? And for security reasons, it actually gives every outbound connection a random source port, right? Even if it were already unique, even if the client chose a unique one, it won't just leave it alone. It'll generally pick a new random one. Very small chance it might pick the same one, but it generally picks a random one. That's for security reasons, just because there's a lot of history with some software that was vulnerable to UDP spoofing and so on. And wasn't doing sufficient source port randomization on its own. So we make sure it's good. We use our own secure random number generators and so on to make sure it's good at that point, right? So that's what's happening for NAT. We have to make that transactional decision. For NLB, we have to make a transactional decision, right? So when that first packet comes in, we have to say, well, which target should handle this, right? We have to pick one. And then we have to remember it, because all those new packets are going to come in for the same flow. We're going to need to send them to the same place, right? And we do this by keeping state. There are ways to try and do this without keeping too much state. But we found that, especially for very long-running connections, and as I mentioned, we have EFS, which can have connections that last months, years, because they're mounted file systems, that this was the way to go. It's pretty cool. One other interesting thing about how Hyperplane works is that these Hyperplane nodes, right? So they're accepting the traffic, they're deciding, making these transactional decisions, they're deciding where the traffic should go. Now, as I mentioned, they're regular EC2 instances, but they don't participate in the mapping system. So the mapping system is abstracted for them. When they get traffic, all they really know is, it's for this Hyperplane resource. That's it. They don't know what the physical mappings on the wire are or anything like that. And that's for pretty strong security reasons. All that's enforced at a lower level in hardware. That's something that we want to maintain very tight control on, make sure there's no possibility of traffic ever being spoofed or anything like that occurring. And so we keep those layers of separation so that really only the decisions, only the things that need to happen on the Hyperplane node happen on the Hyperplane node. OK, so that's what's going on in terms of distributed consensus algorithms and how it makes decisions and what it does with traffic. But there's another cool part of Hyperplane that I want to cover. So Hyperplanes, it's this system that's running. It handles massive volumes of traffic. Peter shared a little about that on Tuesday. It's based on the architecture of the S3 load balancer. We essentially moved that to EC2 and adapted a little to be able to do NAT gateway and so on. So it's really built for very high traffic volumes. And it's embedded in the network, and the network is multi-tenant, right? So it's not like we spin up Hyperplane nodes just for customer A and Hyperplane nodes just for customer B and C and D and so on. These nodes are shared across all customers, lots of parts of the network are, right? Which brings a new challenge. How do we manage this multi-tenancy, right? How do we make sure that customer A doesn't cause problems to customer B? And we call those noisy neighbor problems. No one wants a noisy neighbor, right? That is not what you want. And this is kind of a core expertise for us, right? This is what cloud services are about. We are about delivering the economies of scale and the efficiencies we can bring by everybody sharing a little, right? By having all this big infrastructure that could really only be invested in at that kind of scale. But you still want to give a single tenant experience, right? You still want to make sure the customer A feels like they're the only customer of this platform, right? So how do we do that, right? What's going on? It's pretty cool. So I'm going to go over a simple example. So let's say we have 8 Hyperplane nodes. We have way more, and I'll cover the math a little later with more. But let's say we have 8 for now. So one strategy could be, OK, all 8 are just shared by all of my customers. Customer A, they have a 1 in 8 chance of hitting any particular Hyperplane node, and that's it. There's lots of systems built like that. There's lots of multi-tenant services, lots of web services built like that. It's pretty common, right? But the problem with that is noisy neighbor problems can be extreme, right? You get a really busy customer, flood all 8 nodes, everybody has a bad day. That's not what we want, not what our customers want. I should caveat all I was saying by the capacity of Hyperplane nodes is very, very large. This system's measured in tens of gigabits, can scale to terabits, so it takes a lot to overload it. So I don't want to worry anybody, so I should add that cautionary note. But we plan for worst case scenarios. We want to make sure any noisy neighbor issues are minimized. So another strategy we could do is we could just shard it, right? We could say, I've got 8 nodes. I'm going to have 4 groups of 2, and a quarter of my customer go to group A, a quarter of my customers go to group B, and so on. And now when one customer gives me a bad experience, well, a quarter of my customers have a bad day. That's better than before, right? That's a pretty common pattern. That's sharding, right? A technique. So we actually extend that, and we do something that we call shuffle sharding, which extends that probabilistically. And what we do is we say, OK, I've got 8 nodes. I'm going to give each customer 3. But I'm just going to give them 3 at random, right? And here I've got this customer who's orange. They get those 3 nodes. And I've got another customer that's pink, and they get 3 nodes. There's one that overlaps, right? That one on the bottom is both pink and orange, so they both got assigned the same one, right? And so let's look at what the overlap's like when you use this kind of algorithm, right? So with 8 nodes, choosing 3 at random, the math works out like this, right? There's an 18% chance there'll be no overlap So if I take customer A and customer B at random, there's an 18% chance they won't overlap at all. So that's quite low. There's a 54% chance they'll overlap by one node, so just like that previous slide. 26% chance to, and so on. 2% chance that all three overlap. That's bad, right? That's with 8. But this is probabilistic math. And combinatorial math explodes like crazy. Like when you start using combinatorials and you add numbers, like the numbers just get crazily big. So let's look at a more realistic scenario that uses the kind of numbers Hyperplane's actually designed for. And that's with 100 Hyperplane nodes. And we give a customer 5, right? So now in this model, there's a 77% chance they won't overlap at all, right? A 21% chance of one host overlapping. Less than 2% chance that 2 will overlap, 2 out of 5, right? And so on down. We can actually do a bit better because we assign them, and because we know how we assign them, we can actually make some guarantees and say, OK, we'll remove ones that overlap too much. So we can say, look, no more than 2 are ever going to overlap between two customers. And then we've got resiliency guarantees in the system. Like we can lose 2 nodes, no problem, right? So if a customer has a really bad day, causes this huge burst of traffic, fills all 5 of their nodes for some reason, right? There's a small chance, right, that like 2 of your nodes, like there's a 2% chance that maybe 2 of your nodes are in that set of 5. So it's really small probability, much better than we saw before, right? So that's already great. But we can just lose those 2, right? Those 2 are just taken out of service for you. And the other 3, there's more than enough capacity to carry on. These systems are built in very big increments of capacity. And so you don't notice. Nobody except the originating customer has any kind of a bad day. And actually behind the scenes, if a customer does have a burst event like that, we actually isolate and scale them and start doing all sorts of things that mean even they don't have a bad day. You know, we actually, Hyperplane resources, by default, you know, you provision a Hyperplane resource like NLB or NAT gateway, we generally give you about 5 gigabits per second by default, which is what you get. And then when we scale you, we do it in 5 gigabit per second chunks. Those are very big, right? Very few people ever get into those kind of requirements. As I said, it's based on the S3 load balancer. We've used it with EFS since launch. It's got, you know, sub-millisecond latency, just crazy numbers of things that it can do. You know, it can do millions of connections per second. It's this massive, massively scalable system. You know, we built it for S3, so its numbers are pretty big. The other thing that it's doing, we launched it for customers, like I said yesterday, is Private Link. So all that's happening with Private Link is because all of this is embedded in the network, we can actually provision resources between VPCs, right? So we can have an NLB in VPC-A, or the provider VPC as it's called here, and we can expose that in ENIs. In the client VPC, I'll be talking about this later in the week on Friday. We have a talk that's on Friday about this, where I'll be going into more detail. But that's Hyperplane just making it all happen, right? It can do the stateful tracking even between VPCs, because it's all just built in. That means you can build even more compartmentalized VPCs, like you can have 1 per service, 1 per team, or if you're a service provider, you can now offer services directly into VPCs and so on. And we integrate with the AWS Marketplace. So, you know, if you want to vend a service this way directly into people's private networks, including, like, it can reach their own premises via Direct Connect, which is pretty cool. You know, all this works through the magic of Hyperplane. It's pretty awesome. So the main takeaways from all this that I want you to leave with, VPC is a software-defined network, right? We're doing all this in code. These are just systems running. We've got, you know, our own custom hardware in places. But we're encapping packets. We've got a mapping service. Everything can be controlled programmatically, right? So unlike traditional networks, I don't have to physically label anything. It's all these descriptions. It's hopefully pretty seamless, right? You can just connect to existing networks very easily, integrates with, you know, traditional networks just fine. And now, you know, now that we're revealing a bit more about Hyperplane, as Peter did on Tuesday, you know, we can reveal that, you know, there's a lot of first-class support for flows that's going on in VPC, a lot that's happening to be able to manage and balance traffic at enormous scale. It's pretty cool. That's all the details I have. Hopefully that was interesting. There are other sessions worth going to. if you want to find more about what's going on with VPC under the hood. And thank you very much for coming. If you've got any questions, I'll be just off stage at the end. And yeah, thanks again.